All right, so we're just going to pick up right where we left off on our notes from Wednesday. And so on Wednesday, we started some practice problems. And in this problem, we have an aerosol can with a given pressure at a certain temperature. And we wanted to know what the pressure would be when we heat up the can to 450 degrees C. So let's plug in the information that we know. We know that the original pressure is 1.5 atmospheres. We're looking for our new pressure, and our original temperature is 298.15. And remember, we took our 25 degrees and converted to Kelvin because PubNert is only true when the temperature is in Kelvin. Otherwise, it's not a linear relationship. We also converted our new temperature to Kelvin, and then we're going to cross multiply and divide to solve for our new pressure. And when you do that, you get a pressure of 3.6 atmospheres, which is quite a bit larger than what we started with. And this is why on an aerosol can, it always says do not incinerate, right? So don't put it in a fire like people like to do, because the pressure goes way up, and so it would make the can explode. So that's what that problem was all about. Let's look at the next problem together. So we have an aerosol spray can with a volume that's given, so we'll underline our volume. Then we have the 3.18 grams of propane gas. So if we're given the grams, what that means is we're going to have to figure out how many moles this is. And so we can solve for the moles if we know how many grams we have and we know the molar mass of the propane. So 1 mole of propane has a mass of 44.094 grams. So this gives us 0.0721 moles of our gas. So currently we have 2 of our 4 variables, the volume, which is 456 milliliters, and we know that volume needs to be in liters, so we'll divide by 1,000 and we get 0.456 liters. Let's look at the rest of the problem. It says if the can's at 23 degrees C, so we know that's our temperature, so we're going to add 273.5 right away. So that'll give us 296.15 Kelvin. And we are looking for the pressure in the can. So we always start with PubNert, but in this case we're rearranging to solve for pressure. So pressure is equal to the moles, N, times the gas constant, R, times the temperature, all divided by the volume. So let's plug in all the information we have. The moles we solved for from the grams, 0.0721 moles. We have the R value, 0.08206 liters times atmospheres over mole Kelvin. And we got our temperature in units of Kelvin, so that'll cancel, 296.15. And our volume was given in milliliters, which we converted to liters, so it's 0.456 liters. So we know that when we cancel all our units, we'll be left with atmospheres for our pressure, and we get 3.84 atmospheres of pressure. So it's fairly pressurized so that it fits into this small volume container and can be stored and shipped easily. What if instead of pressurizing the can, we didn't put it under pressure and just left it at 1 atmosphere, because that's what STP means, that it's 1 atmosphere of pressure. Let's see what this does. So we know that if we have 0.0721 moles of our gas, at STP we know that this has a conversion factor of 22.4 liters per 1 mole. So we can go ahead and solve for the volume, and we get a volume of 1.62 liters. So if you compare this with what the volume is when it's pressurized, you can see why we would want to pressurize it, because then it will fit in a much smaller can, which is more efficient for shipping and storage. All right, let's look at problem number 3. So it says a person accidentally swallows a drop of liquid oxygen which has a density of 1.4 1.149 grams per milliliter. So it looks like we're not really given much information yet. Assuming the drop has a volume of 0.050 mils, what volume of gas will be produced in the person's stomach at body temperature and a certain pressure? So it looks like we definitely have at least two of our variables. We know temperature is 37 degrees C. We know that we're going to convert that to Kelvin. So the temperature will be 310.15 K. We know that the pressure is 1 atmosphere, which makes our lives a lot easier. And we are going to be solving for the volume. But it looks like we have two pieces of information about volume and none about moles. So how do we deal with that? Well, we know that we were given the volume of the liquid and the density of the liquid. So that means that we'll be able to solve for the mass and then the moles. And we're going to see how when the liquid changes to the gas, how that affects the volume. So to solve for the moles, we're going to start with the milliliters of our liquid, and we'll use the density to convert that to grams. We know the thing we're thinking about is oxygen, so we'll use the molar mass of oxygen to calculate the moles of oxygen. So we get 0.0018 moles of oxygen. And now we're going to PubNert to solve for the volume given the amounts that we have here in the problem, the different quantities. So let's plug in everything we know. We know that the moles is 0.0018 moles. We know the R value is a constant, 0.08206 liters times atmospheres over mole Kelvin. And we know that the temperature is 310.15. And I underlined the 0 to remind us that we have 3 sig figs. And then our pressure is 1.0 atmospheres. So when we solve, we get a volume of 0.046 liters, which if you want to directly compare to what we started with, that's 46 milliliters of our gas versus the 0.050 milliliters of our liquid. And the point of this problem is to emphasize to you how different something behaves in the different states. So imagine a tiny drop of liquid expands to a much, much larger volume of gas. And that's why liquid oxygen is incredibly explosive and leads to a lot of laboratory accidents. All right, let's do one of our molar mass problems, and I'll leave you to do problems 5 and 6 on your own and post the key on Canvas. So let's look at the molar mass problem. So our molar mass problem says that we have 6.35 grams, and it occupies a volume of 1 liter. So V equals 1 liter. We have a temperature, and that's 22 degrees C. And we'll add 273.15 to get our temperature. So that's 295.15 Kelvin. And we're given a pressure in units of torr. So pressure is 743 torr. But we're going to go ahead and convert that to atmospheres so we can PubNert. So 1 atmosphere is 760 torr. So if we do the calculation, gotta grab my trusty calculator. 743 divided by 760 gives us 0.978 atmospheres. So for the molar mass, we know that molar mass is defined as grams per mole, and the only variable we didn't solve for in PubNert is N, so N is our question mark. Let's solve for the moles using PubNert. So according to our algebra, N is equal to PV over R times T. So let's plug in our variables. The pressure is 0.978 atmospheres. Volume is 1 liter. The R value is 0.08206 liters times atmospheres over mole Kelvin. And the temperature in this one is 295.15 Kelvin. So we're going to solve for the moles. So 0.978 divided by 0.08206 divided by 295.15. And we get let's color code appropriately. We're in green. 0.0404 moles of our gas. So that means that when we find our molar mass, we're going to take the grams that we were given, 6.345 grams, divided by the moles. Sorry, we ran out of space a little bit here. And we get 157 grams per mole with 3 sig figs because that's what we had from our pressure and volume. So we would be able to identify a gas that way. So try number 5 and 6 on your own for practice. And let's move on to the next topic. So the next topic in our notes is gas mixtures. So a lot of the time when we have gases, they don't exist